Okay, so let's solve this practice problem. So we read through it here. It says um, this elbow, the structure AB, all right, is attached to a smooth square rod at A, all right, with a loose fitting collar. And it's also supported by this cable BC. All right. The collar, as it says here, allows motion along the pole only. If you look at the axes, this is the z-axis. So motion is possible in this direction since the collar is loosely fitting, but all other motion is prevented. In other words, it cannot translate in the y direction. And make sure you note the axes. Here's the y direction. It cannot translate in the x direction, and it also cannot rotate about any one of the three axes. All right. So the question then is saying, all right, determine the reactions at A, all of the components of the reaction at A, and also the tension in cable BC. There's also a force that's being applied here, vertically downward, and as the problem statement says, that force is equal to minus 300 K. All right, the units are pounds. Okay, so the first thing we do, as always, we draw the free body diagram. So let me do that over here. The free body diagram looks something like this. All right. So this is F, right, the force that's being applied. And since there was no letter on this, I'm going to call that point D. This is point B right there. All right, so here's TBC. All right, so there's the forces that are acting, force acting at D, force acting at B. The cable tension is acting at B. And then at A, again, I've removed the collar and I replaced it by what the collar is doing at A. All right, so let me put the axes on here. Here's Z, here's Y, and this is X going in this direction. Okay, so as far as that collar is concerned, as we said, it cannot translate in any one of the directions except the Z, except vertical. All right, so what I have then, I have an AX component of the reaction force. I have an AY component of the reaction force. Extend this a little bit. All right, it cannot rotate either, so I've got three components of the reaction moment. I've got MRAZ, okay, I've got MRAY, and I've got MRAX, okay. So there's my free body diagram. Again, I need to put dimensions on here to make it complete. But I'm just going to skip that for now. But of course, on your exam, make sure that you have a complete free body diagram. Okay. So then what I have is this. Okay. So the first thing I like to do is I write the vector equations, right, that need to be satisfied for equilibrium. So what that is then is sigma F is equal to 0. The vector equations. All right, sigma F is equal to 0. Okay, so I have the reaction at A, right, with its two components. I have TBC, and I have F, right, is equal to 0. So there's the vector sum of the forces. Okay, so again, before I go any further, I just note that A, the reaction force is AXI plus AYJ, okay? All right, there is no Y component to the reaction force. So I look at this, and I say my force equation, what I have is I've got 1, 2, 3 unknowns, all right? The magnitude of TBC. So what that immediately tells me is if I solve the force equation, sigma F, the vector sum of the forces is equal to 0, I can determine AX, AY, and TBC. Only 3 unknowns. I have 3 scalar equations of equilibrium, so I can solve for all 3. Right? But before I do that, what I want to do is this. I want to write the moment equation, and just like always, I can sum the moments anywhere. So I'm going to choose, you don't have to do this, I'm going to choose to sum the moments around A. Okay. So the vector sum of the moments about A is equal to 0. So I look at this and I say, well, I've got a moment about A due to this external load, this force being applied there. I have a moment due to the cable tension, moment about A due to the cable tension. And I've got the reaction moment. Very importantly, no matter where you sum the moments, and I stress this, no matter where you sum the moments, the reaction moment, which I've indicated as MRA, the reaction moment is in the equation. So for example, if you chose to sum the moments at D, all right, I'd have a moment due to the reaction force at A. I'd have a moment due to TBC. There would be no moment due to F. And I'd also have the reaction moment. Again, very, very important. No matter where you sum the moments, the reaction moment is in the equation. Because never lose sight of the fact, when I remove that support, I'm replacing the support with what it is doing to the structure. Right? What it's doing to the structure is the reaction force, A, which has the 2 components, and the reaction moment, which has the 3 components. Okay, so when I write my vector equation, okay, so here's MRA, the reaction moment. Then the moment due to the force F, again, you can determine this any of a number of ways, but I'm going to do this RAD, again, using the cross product, RAD cross F. Okay, and then the moment about A due to TBC, RAB cross TBC, or another probably equally as easy to do would be C is up here someplace. I could use RAC cross TBC. Again, that cross product, there's an infinite number of position vectors from A to the line of action of TBC. Okay. I chose B, you could choose C, you could choose any one as long as it's on the line of action of TBC. All right, so I have my moment equation, right? Vector sum of the moments is equal to 0, MRA plus RAD cross F. All right, and then I chose RAB cross TBC is equal to 0. All right, so there's the vector. I think it's a good idea to always write the equations first, the vector equations first, and then see how many unknowns are in here. MRA, okay, is a Cartesian vector, so it's MRAXI plus MRAYJ plus MRACK. All right, so there's 3 unknowns here. All right, the 3 components of the reaction moment. Okay, and I also have 1 unknown here, the cable tension. So in the moment equation, there's 4 unknowns. I only have 3 scalar equations that need to be satisfied. So I look at this and I say, well, I might get some of them, but I can't get them all, right? Because there's 4 unknowns, only 3 equations. But that's okay, because my force equation, right, there's only 3 unknowns, AX, AY, and TBC, so I can get them, okay? It's also convenient to write the coordinates, makes it a little bit easier when you're doing the arithmetic. Okay, so what I have is, these are in feet. Is that right? Yeah, these are in feet. So A is 0, 0, 0, right? The origin is at A. Again, note the layout, or note the orientation of the axes. So B is 1240. C, these are in feet, 086. And D, okay, D is 1200. Okay. Again, it's convenient to do this before you start solving the equations, writing terms and so on and so forth, rather than always referring back to the free body diagram. Makes no difference. You can do whatever you want. Anyway, so let's go ahead now. So I know what I want to do. Okay. So I'm going to solve the force equation first, because there's only 3 unknowns. Okay. So sigma F is equal to 0. Okay. I can get, again, just repeating it, but I can get AX, AY, the 2 components of the reaction force, and the magnitude of the cable tension. All right. But what I first need to do, if I go back to my vector equation here, right, TBC, so I need to express TBC as a Cartesian vector. Right? I already have A as a Cartesian vector. Okay, that's just AXI plus AYJ, but I need TBC. So TBC, as we're well aware, for any vector, TBC is equal to TBC, the magnitude times its unit vector. All right, do that. And that's TBC. Its unit vector is the same as the unit vector with the position vector from B to C. All right, so that's RBC divided by its magnitude. Okay, and then using the coordinates, this is TBC, that's the magnitude, and then minus 12i plus 4j plus 6k. Okay, divided by the magnitude, which is 12 squared plus 4 squared plus 6 squared to the 1/2. Okay, a little bit of arithmetic. I get TBC, the vector TBC is equal to its magnitude and its unit vector. The denominator comes out to be 49. Take the square root, that's 7, so it's minus 6/7 I plus 2/7 j plus 3/7 k. Of course, you could use your calculator to determine what 6/7 is and so forth. Makes no difference. All right, so I have that. So there's TBC. Okay, I know, again, A is equal to AXI plus AYJ. Okay, again, no Z component because motion is possible in the Z direction. So now all I've got to do is collect terms. All right, for my 3 scalar equation, sigma fx is equal to 0. It tells me AX minus 6/7 TBC is equal to 0. There's my x equation, my y equation. Sigma fy is equal to 0. It says AY. Okay, plus 2/7 TBC is equal to 0. And then last but not least, sigma of z is equal to 0. All right, tells me that minus 300, okay, because again, don't forget that force, okay, is minus 300k. All right, so my z, when I sum the components in the z direction, I have minus 300 plus 3/7 TBC is equal to 0. All right, the z equation I can solve. TBC is equal to 700 pounds. Okay, and that, there's the magnitude of the cable tension. I take 700, I go into Fy and the sigma Fx and the sigma Fy equation. All right, then I solve for AY. AY is minus 200 pounds. And AX is 600 pounds. Okay, so I solve for TBC first, and then I go into the X and Y equations, and I get the 2 components of the reaction force. Okay, so that now there's 3 of the 6 unknowns have been solved for. Okay, now as long as I'm here, I know I need TBC as a Cartesian vector for the moment equations. So again, that is just TBC UBC. UBC is here in parentheses. TBC is 300, so I do a little bit of arithmetic, and I get TBC is minus 600I plus 200J, right, plus 300K. Okay, pounds. So there is the cable tension expressed as a Cartesian vector. All right. So again, I've got AX, I've got AY, and I got TBC from the solution of the vector sum of the forces is equal to 0. All right. So now I turn my attention to the moment equation. Okay. And I go back to what I had previously. Oops. Okay. What I had previously, again, looking at the vector sum of the moments about A. MRA, the three components, MRAX, MRAY, MRAZ. All right. I already know what TBC is, so now there's only three unknowns in the sigma MA equation. So I can go ahead and solve that. Okay. So I have two cross products that need to be done here. RAD cross F, again, that external load that's applied at D, and RAB cross TBC. All right. Now, in order to do this cross product, obviously, that's why I needed to have the cable tension expressed as a Cartesian vector. So let's do those two cross products. Okay. RAD is 12I. So RAD cross F. I do it as one 3x3 determinant. I know some of you do it as three 2x2s. Makes no difference. IJK. All right. 1200. Again, never lose sight, never forget. It's R cross F. It is not F cross R. So the second row are the components of the position vector, RAD, so that's 1200. And then the third row is F, which is 00 minus 300. Okay. Okay. If you expand that, you get RAD cross F is equal to 3600. I'm sorry, not minus 3600. Is equal to 3600 J. Okay. 3600 J. Okay. And if you look at this, this makes sense. If you look at, go back to the diagram, go back to this force is only tending to cause a rotation about the y-axis, not about the x-axis nor the z-axis. So it makes sense that there's only the y component. Okay. All right. That takes care of one of the terms, or one of the cross products. The next one, RAB cross TBC. Okay. RAB, this is 12I plus 4J. Back at the diagram. All right. The position vector from A to B. It's 12 in the positive x direction, 4 in the positive y direction. So it's 12I plus 4J. All right. So RAB cross TBC, then set up the determinant and expand it, IJK. Second row, 1240. Okay. Third term the third row is the components of TBC. So that's minus 600, 200, and 300. Right. So I've got. Okay. Do the expansion. You get this, comes out to be is 1200I minus 3600J plus 4800K. Okay. So that is the moment about A caused by TBC. And again, it's always good to make sure it makes any sense. TBC, you can just hopefully look at this and say, well, yeah, okay, TBC, this cable tension is going to tend to cause a rotation about all three of the axes. All right. And so this is what you see here, 1200I, the tendency for rotation about the x-axis, the y-axis, and the z-axis. All right. All right. So, and again, MRA is equal to MRAX, again expressed as a Cartesian vector, I plus MRA YJ plus MRZK, right? So I have now all three of the terms in the vector sum of the moments about A equation. So now all I do, just like I did for the force equation, collect the components. So the components of the moments about X is MRAX plus 1200 is equal to 0. So the component, the X component of the reaction moment is minus 1200 pound-feet. Don't forget the units. All right. sigma MAY, collect the Y terms, that's MRAY, okay, plus 3,600, okay, here, minus 3,600 from here, all right, so MRAY, the Y component of the reaction moment is 0, okay. So again, what that physically means is that the tendency for rotation about the y-axis caused by this external force at F is equal and opposite to the tendency for rotation about the y-axis caused by the cable tension, TBC. So the component of the reaction moment then is equal to 0. And finally, I collect the z terms. MAZ is equal to 0. All right, so that's MRAZ, all right, plus 4,800 is equal to 0. So MRAZ is equal to minus 4,800 pound-feet. Okay, so there, problem solved. Got the 6 components, or the six quantities that I need. All right, go back to this. AX, AY, the component of the reaction moments. All right, I have an MRA. I always like to put the R in there to kind of make sure I know that it's a reaction moment. So MRAX, MRAY, and MRAZ. So I've got all 3 of them. Okay. So, and again, don't lose sight of the fact what these physically mean. Okay, that the force and the cable tension is tending to translate that structure in the X and Y directions. Okay, and it's that support that prevents this this translation. It's tending to rotate, these forces F and TBC is tending to rotate the structure about the X-axis and the Z-axis, not about the Y-axis, just because they counteract each other. All right, but again, what this support is needed to do is to counteract, to prevent the rotation about the 3 axes. Okay, so that takes care of problem 4 of the example problems.